Okay, all right, let's get started. So first thing, the midterm should be returned, right? So you should see the midterm, your midterm grade, and the solution was attached in an email sent out last night. So take a look at your graded midterm. Make sure I added up the points correctly, right? So, and if you have any questions, let me know. So for each individual concerns, of course, we can talk about that, after this class or in the office hour. But in general, any comments about the midterm? Okay, so the final will be a slightly shorter version of the midterm, basically, concentrated on the last part, the second half of the class. Okay, and some general notes about your solutions. So make sure that the answer is highlighted clearly, especially since this is take home and people tend to write a lot of notes around it. So make sure I can find the number easily, right? So sometimes it takes quite a while to find where exactly is the answer to the question. And also, if you're using quite a number of people wrote their midterm basically using a notebook, using from sort of code. That's fine, but in those cases, please round. Okay, there are people, with answer that's up to 12 decimal places, right? So if that's the machine position, please, round it to a reasonable number of digits. Okay, right? So remember that, for the final, right? Circle your answer. However you hand it in, make sure the answer to the question is obvious. Which of the numbers is the answer to the question? No. I think there's a few people who basically wrote, I'm not sure. So I'm going to give you two versions of how I think I should answer the question. Now go ahead and pick which one you think was correct. So that's not going to work, right? So if you're not sure, you still need to pick an answer in the midterm, right? So you can write about why you think it may be wrong or you think you should have done the question, but just make sure that you pick a number as a solution. And make sure I can read it clearly. And if you're using, if you're just printing out a lot of basically a lot of coding from a notebook, that's fine. But in that case, please round. Okay, so please, make it reasonable. Especially, for example, people use to generate the Y matrix using computer program, and somehow that matrix, each number in that matrix has 10 decimal places, right? So those make gradings difficult. Okay, so other than that, I think people did a great job on the midterm, and final will be similar style. Any comments, questions on the midterm? Okay, so take a look at the solution. Look at the look at your points again. Make sure add up correctly. Or if I missed part of the, I think there's a few people who are missing parts of problems. So if I missed a part of, if I didn't see it, let me know. And also another thing for the final, please upload one file. Okay, please upload one file. There's people who uploaded multiple files, and it's not always obvious from Canvas. There's multiple files. Okay, so if you can, upload one file and not one per question. And in the chat, will the final be a little bit shorter? Yeah, so the final will be shorter. Right? So this is one day, so it'll be a shorter version of the midterm. So it'll be, I don't know, ballpark-wise, 75%, 80% of the length. Right, so I haven't made the final yet, but the midterm was out of 115, so the final will be out of say 95 or something somewhere around that. Okay, and also for the final, there'll be no late submission, except if you let me know beforehand. Okay, so the midterm, there are some late submissions. I know some people mess up the time zone, some people miss it by a couple minutes. For the final, if you don't tell me you'll be late, there'll be cannot accept late submissions. So the rules associated with finals are quite strict. I have to turn it around relatively soon, so please submit on time. Okay. Other questions? Okay, and one other thing is, I'm not sure if you can control this, but try to make it so the sort of the size of the file is correct, so the zoom of the file is correct. There are some files that's the fonts are super large. Some files where it's just impossible to read the solution. So if you can make sure it's sort of readable, the PDF is readable, right? I think there's one there's one midterm solution where I can't read a lot of the answer. Okay, so it's just so small that I can't read it. So make sure if you can make sure it's reasonably readable. Okay. All right, so that's the midterm. So if no issues with the midterm, then let's recap what we did last time. Okay, let's look at what we did last time. So last time, remember we talked about unit commitment, right? Unit commitment basically is a point where we have 0, 1 binary decisions, right? So this is, we have a generator, can be on or off. So this is binary. And from that, we need to determine the least cost solution, taking into account that, whether the generator is on or off. Right? So which generator should be turned on, which generator should be turned off. Okay. So if you look at the homework, right? So basically homework had this example of a question where it says that, given a system with a load with 3 generators, G1, G2, G3, right? Find out the combination of the on-off generators and find out the least cost solution, right? So figure out this least cost solution. And this generally ends up to be you need to make a table. For example, this is 1, 2, 3. You have on-off status, things like this, and we need the generation, the cost. Okay, so normally to solve this type of problems, you make a table and you read off from this table. Okay. And it's important to know how to make this table. So for sure, in the final, you'll see some question like this. Okay, so make sure that you can do this reasonably efficiently. And make sure you practice enough, or what's going on, to generate this table reasonably efficiently. Okay, so this will be part of the final. So if you think about the final, what we have is basically solving various optimization problems. Right? So the final will not be very connected to the first part of the class. Right? We won't, for example, be looking at 3-phase transformers and things like this. But what we can look at is, for example, given a system makes a Y matrix, or given a system, figure out the topology. Right? So this is a tough question we can ask. We can ask for different optimization problems, right? We can ask for all this kind of questions. So make sure you're familiar with this type of material. Okay? So this class will still cover somewhat new material. Then we'll do a sort of short review on Wednesday. We'll do a short review on Wednesday. to remind you what kind of problem you may see on the final, right? And if you forgot something, what you should review, okay, for the course. But for unit commitment, this kind of question, be sure to be confident that you can generate a table like this, right? So these are part of the exam. Okay. So of course, so for us, it will be table generation, right? Mostly for us, it will be table generation. Of course, in practice, we don't generate tables, right? There's no way you can generate a table for a problem of any practical size. So in practice, what unit commitment problem boils down to, the sort of name is called a mixed integer linear programming. So there's reasons for all these names. So mixed, right? So the word mixed comes in from the fact that we have mixed integer, or if you look at mixed integer, so this is both integer variables and continuous variables. Right? So when we solve unit commitment, we have both, the on-off status of the generators and how much power each generator is generating if they're on. And so this is called, so we're looking for both the integer variable solutions and the continuous variable solutions. So this is called, so this is a mixed integer, meaning both are there. Linear programming, this is just a name for essentially economic dispatch. Okay, so we're looking at dispatch problem. We're looking at mixed integer economic dispatch problem. So this is called a MIP, right? MILP. And there's various ways to solve a mixed integer problem. There's quite a number of algorithms for this. And none of them have really guarantees per se, because these are combinatorial problems. So there's no formal guarantee of you will be able to solve a MIP problem. And there are efficient solvers in the sense that there are tried and true heuristics to solve problems this way. Okay, there's so many solvers that tend to work well in practice, but often, do not, there's again no theoretical guarantee of whether they work or not. Okay, so it's really sort of more of a question mark. Are there efficient solvers? And people are finding new ways to solve this sort of mixed integer problems, right? So, and there's really sort of very specific heuristics. There's sort of a number of specific heuristics we can solve. We use to solve this kind of problems. We're not going to cover this heuristics in this class. They require quite a bit of optimization knowledge to get to know, why heuristics works and why, when can you expect something to be good, when can you expect something to be bad. Okay, so this is sort of again itself a very large field. Okay, so in this class, we're going to look at a simple example. Again, we're going to think about why the problem is hard and understand the complexity of it. And then if you are interested in this sort of topic, there are other classes for graduate level classes you can take that really goes into how do you solve this kind of integer problems. So before looking at an example, let's actually think about let's look at a simple heuristic. All right, so and we'll see why this heuristic is actually not so good. Okay, so for example, let's say you have a problem, and the problem is in the form of mean f of x. Okay, so think of x now as integer variables, and let's say we have a bunch of constraints, and then at the end of the day we have x equal to 0 to 1. Okay, we have x is inside 0. Xi is either 0 or 1. So you may be tempted to use the following heuristic. You may be tempted to say the following. Right? You may say, okay, maybe this is roughly similar okay. So a temptation is often to say, hey, maybe I can relax the integer variables into continuous valued variables, right? Since, being between 0 to 1 makes the problem hard. So let's relax them into a continuous range between 0 to 1. Okay? Maybe this is an easier solution, and this is a much easier problem, and maybe solving this problem give us a some hint of what the actual solution is. For example, let's say you can solve this problem, then maybe you can say, how about rounding to 0 or 1, right? So one easy way is to solve this continuous problem. So you get some number, real number between 0 and 1. And you can say, okay, maybe let me just round it based on the value, right? Less than 0.5, round it to 0. If it's close to 1 or more than 0.5, let's round it to 1. Right? Let's see how well does this kind of thing work. So how well do you think this will perform? This kind of rounding procedure. Should we expect this to perform well? Is there some expectation that this kind of method will do well? And assume it's continuous, and let's solve it, just round it. Would you expect this to do reasonably well, this kind of rounding strategy?
With a large system, I would expect it to do well.
Sorry, can you repeat that?
With a large system, I would expect it to do well. I think the averaging of the rounding up and rounding down would be close enough.
Right, so that's a common intuition people have, right? To say, if I have lots of variables, some of them are rounded up, some are rounded down, and maybe at the end of the day, the solution is not too bad. So that intuition turns out to be not correct. So this almost never works. Although to be fair, there are exceptions, and the exceptions themselves, when rounding can work, often points to sort of deep structures about the problem. Okay? There are cases when rounding works, but that normally has to do with the special structure of the problem. And those are sort of quite deep. Those are quite deep, why rounding works. There are sort of notable exceptions. And again, many people who spend entire career studies when these exceptions occur. But in practice, rounding almost never works. Rounding almost never works. The reason rounding almost never works is these constraints. Once you round, what happens is you almost never satisfy any of the constraints. Right? So you may think for the objective function, some are rounded up, some are rounded down. So at the end of the day, maybe the objective function value doesn't change so much. But the constraints is almost impossible to get constraints to hold. So you have a large problem, you solve this in continuous way, then you round. As more often than not that most of the constraints are not holding anymore. Right? So this is the problem with rounding. And this is again why sort of solving integer problems is far from trivial, far from trivial. So a lot of times our intuition, which so we have people tend to have quite good intuition for continuous problems, but for discrete problems or combinatorial problems, often our intuition is not great. Okay? So that's why again, you be careful when you solve integer problems. So those, to learn how to deal with this and to learn sort of better heuristics in rounding, again, is way beyond the topic of this class. But for this class, again, when you do your problem, just make sure you just exhaustively check everything. Don't try to find the don't try to save time and not check some cases. For us, our problem is small enough. The best way to deal with them is still to exhaustively just check everything for us. Right? So again, so continue from last time. As last time, remember what we covered, and the problem in your homework is just for one time period. Okay? But often for unit commitment, the decision is coupled over multiple time periods. Okay, so here we're going to look at one small example of what solving the problem looks like when we're looking at more than one time period. Okay, let's say we're looking at multiple time periods. And here, let's say we have 3 generators. Okay, we again have 3 generators. And they have some minimum generation, maximum generation. They have minimum up, minimum down times. Okay, so this is right. So these constraints basically couples over time, right? So they couple over time because, for example, generator A, it says if you use generator A, has to be on for all 3 hours. If you turn here, it says if you use generator B, has to be on at least 2 consecutive hours. Okay, so these are sort of the time coupling decisions. For simplicity, we'll have we'll have 0 no load cost. And for marginal cost, so these are just linear cost. Okay, so we won't have a quadratic cost. We just have everything being linear. They have different startup costs, and they start off at the different conditions, right? On-off conditions. So they have different initial status. So this is the generator data we have.
Professor?
Yeah, go ahead.
I see the marginal cost is that the lambda times the p.
No, right? We don't know the lambda. There's no lambda yet for this problem. We haven't solved it. So this is, so remember so for example, CA, this will just be the marginal cost. Let's say call this call this PA or PA. Let's call this alpha A times PA, right? So this alpha A is the linear coefficient. So this is, for example, $10 per megawatt hour, right? So here, instead of a quadratic cost function, we'll just have a linear cost function.
Okay.
Right? Make things easier to look at.
And why is no load cost?
No low cost? No low cost, so remember, before we have something, right? We always have the constant plus the part that has to do with the power generation. Yes. So here again, to make things more easier, we just have no low cost being 0. Okay. So we don't have to add we don't have to add that cost.
Because I was thinking about the no load cost is the same as the startup cost.
No load cost is not a startup cost, right? Startup cost, you only have a startup cost when you go from off to on, right? When you're starting off the unit. So if you're transitioning from, so let's say you have a generator. If you're transitioning from off to on, this has a one-time startup cost.
Okay.
One time. Okay. Only one time. At every time, you have no load cost.
Oh, every time no load cost is that constant in the quadratic function.
Yeah, so that's a constant there. But as happens at every time instant. So if you're on, you always have the no load cost. Or the startup, it just goes from turning off to on. So it's a one-time cost.
Okay, thank you.
Yeah, so normally we will have some no load cost, but in this problem, we'll just assume it's 0 for simplicity. Okay, simplicity. Okay. Good. Any other questions? Okay, good. So the reason we have linear cost, right? So this is basically linear cost making solve the problem easy, right? This says linear cost basically always use the cheapest one to max capacity. Okay, so because the cost is linear, so if A is available, if generator A is on, we should always use A. If generator, if A runs out of capacity, if generator B is on, we should always prefer generator B compared to generator C. So the cost is not quadratic, right? So the derivative of this cost is a constant. So you basically just use the cheaper one. If the cheaper one is there, we use the cheaper one. If generator A is not on or runs out of capacity, we can then go to generator B, then to generator C. So this is a cost. And then we're going to look at a 3-hour hourly demand. So this is 150 going to 300 going to 200. Okay, so we have 3 hours and they have this kind of demand. Right. So again, for unit commitment, even though the demand varies within an hour, our assumption will be we'll just assume everything within an hour is constant. Okay, so the demand changes from 150 to 300 to 200. So this is our demand. Okay. So then let's look at how we solve the problem. Okay, let's look at solve the problem. And for this kind of small problems, it's better to think of this in a graphic way. Okay, a graphic way. So the way we're going to think of this kind of problem is to look at, right, there are 8 combinations. Okay, there are 8 combinations associated with the status of the units. Okay, so each row or each circle here is a unit status combination. Okay, is a combination, right? And as we have seen from last class and this week's homework, that not all combinations are feasible. Okay? Not all combinations are feasible. All right. So for this 3 time periods and these combinations, the blue dots are the feasible ones. Okay? So the blue. So here we have not enough generation, right? So if you look at the combination, for example, 0, 1, 0, the maximum generation is only 100, but our load is 150. So there's not enough power, not enough total generation to meet the demand. So they are not infeasible. If you look at this one, this is too much generation, okay? Because the minimum is more than the load. Okay, so these are not feasible. So only the 3 blue dots, the 3 ones, right? The blue dots are feasible. Okay? Only the blue dots are feasible. Any question with this diagram? So you'll see this diagram. So this example basically just go through the diagram. So let's be clear about this diagram. Okay. Right, so we have 3 time periods. This is time period 1, time period 2, time period 3. Right. So these are the loads. Okay. For each time period, there are only a certain number of combinations that are feasible for these loads. Right. So for time period 1, only these 2 combinations are feasible. For time period 2, these combinations, the top 3 combinations are feasible. For time period 3, sort of the middle 3 combinations are feasible. So these are sort of the feasible combinations, right? These are the possibilities we can have. Any question with this diagram? Usually this diagram? Yeah.
Hi, Professor.
Yeah, go ahead.
Do you see the 101?
Mm-hmm.
So, okay. So which means the generator 2 and 3 is turn on and 1 is turn off.
101 means A is on, B is off, C is on, right? 101.
101 is the A, so the blue dot means the on or off. I think blue dot.
No. Blue dot do not mean the on and off. Blue dot do not mean on and off. So let's be clear about this, right? So no. This is not. These are the time periods. This is time. 1, time 2, time 3. Right. So remember our load. We have 3 hours.
Yes.
So this is hour 1,
Mm-hmm.
hour 2, and hour 3. So 101 is here. 101 as generator A is on, B is off, C is on.
Mm-hmm. Oh, so which means like the P minimum and P maximum. So hour 1 is not feasible for this solution.
No, this solution is not feasible for hour 1. Right?
Okay.
Not hour 1 is not feasible, right? So we're not optimizing over load, right? We're just optimizing over generation. So load is 150, which means this combination is not feasible for this load.
Okay. Oh, thank you.
Okay, yeah. So any other questions for this? It's good to understand, yeah, this diagram. So we're gonna solve this problem basically by drawing this diagram, by drawing arrows on this diagram. Any other questions? Okay. All right, so if we're comfortable with this diagram, then what does a solution look like? So what is actually a solution? If this is a diagram, right? So a solution is basically a transition path between the dots, right? So for example, this is a potential feasible solution, right? Because we're going from a feasible blue dot for hour 1 to a feasible blue dot for hour 2 to a feasible solution to hour 3. Okay, so this path by itself is a feasible, right? Is basically a possible solution to our problem. Okay? What this path means is in hour 1, we'll take this combination of 100, we'll transition to 110 for time 2, we'll transition to 100 again for time 3. So this is our example of a possible solution. So this is a possible solution. So what we're doing then is what we're asking for is, so basically, there are many possible paths in this problem, right? We could be transitioning all around these paths. So our goal is basically to figure out the optimal path, right? To figure out the sort of the optimal combination of units. Okay? Right, so our goal is to the least cost path. Okay? Our goal is to figure this out. Okay? So we're going from we're going from the initial state to the right. So we're going from initial state, and we want to figure out the optimal solution for hour 1, hour 2, hour 3. So we can think of this as transitioning between different combinations of generators. And each particular transition gives us a path in this diagram. Our goal is to figure out what is the optimal path. Okay, and any questions with the idea, with the goal? Right, so we'll just do this graphically, right? So we'll basically graphically figure out the path. Okay, so the tricky thing here is that, again, we need to know that not every path is possible. Not every path is possible because of minimum up and minimum down time requirements. Okay? Because of minimum up and minimum down. Okay? So, right, what we said is, if you look at this says A, if turned off, needs to be off for 3 hours. Okay, so if we're going to turn it off, let's turn off for 3 entire hours. Okay. So basically, these paths, these dotted lines are not feasible again, because they require turning generator A on and off. They require turning generator A off, then immediately on again. So these are not possible, right? Because the constraint that if A is off, it has to be off for 3 hours. So we rule out some possible paths in the problem. Similarly, okay, so we rule this out. So these are some sort of infeasible paths we have here. Then again, because B has to be off, right? So this says if B is turned on, needs to be on for 2 hours. Okay, so then this eliminated these are dotted lines, because these dotted lines are not feasible. They require B to be on for, they require turning B on and then immediately turning B off. So these are not possible. Okay. So what we get is basically, we get these feasible transitions. Okay. Right, so we get these feasible transitions. So our feasible transitions are all the purple arrows that's left over. Yeah, all these purple arrows that's left over for our feasible transitions. Okay. Any questions about how we get these arrows? Right, so you basically rule out possibilities, right? First, we ruled out combinations where that is not feasible for the load. Then we ruled out transitions that are not feasible because of minimum up and minimum down requirements on the generators. We rule these out. So what we're left over is all these sort of purple paths that are possible for us. Those are possible. Any questions about this procedure? Okay, so once we rule all this out, then basically we have then we have possibilities, right? Then we have sort of all these are feasible. So the way we solve our problem is we're going to look at every one of them. Right? So these are all possible. These are all the possibilities that we have. So let's figure out, what are the cost for each one of these. Okay, let's look at the cost for each one of these. Okay. So we're going to look at the economic dispatch basically for all of these. Okay, we're going to look at economic dispatch. Right. So the way, right? So there are 7 states, right? There are 7 sort of circles that we can live in. So we're gonna exhaustively go through all of them and solve economic dispatch. Right? We're gonna solve economic dispatch. Right? So, right, for example, state 1, if you go back to this diagram, you figure out generator A is on, B off, C off. Then we can compute the cost. Right? So from each of these states, we can compute the cost. Okay? We're going to compute the cost. So this basically gives us the operating cost, right? So if we're operating at the states, these are our operating costs. Okay? We can just draw them. We can write them down under this notes. So the cost, if we go pass through this node, or we go pass through this circle, we'll have this kind of cost. Then we can add in the startup cost, right? We can add in the startup cost, because whenever we start a unit, we have some cost. So if we transition, we basically have different cost levels. So this arrow, for example, going from 1 to 2. This goes from 100 for the generator status to 101. So this turns generator C on. So this has a cost of 100 if we follow this path. Similarly, if we go from 1 to 3, this has a cost of 600. This line has a cost of 700 because we're turning generator B and C on at the same time. Okay, so these are the startup costs. Right? We're factoring startup of cost. Basically, each time we go from 1 hour to the next hour, we're turning some generator on, turning some generators off. We're gonna, we may have different costs depending on which generator we start. So similarly, if you look at the transition, here going from 2 to 7, we are turning generator B on. So this arrow has another $600 startup cost. Okay. Okay, so then once we have the startup cost, we can just compute the accumulated cost. Basically, what is the total cost we have for this problem? What is the total cost? And then we can, yeah, go ahead.
So when we're starting from the initial to the status 1, so we turn on the generator 1, so it's also cost for the 1,000 from initial
No,
to 1.
for the initial cost of generator 1 is on, right? For the initial state. So our initial status as generator 1 is on. So our initial state is already 100.
Okay, 1's already on.
Yeah, 1's already on. Yeah, generator A is already on. So there's no cost there. Generator A is already on. Okay, so this is all the different, you're basically adding all different costs. You look at the cumulative cost at the end, as the hour 3. So we have 3 different ones. Then you pick the one with the lowest cost. Okay? Then you pick the one with the lowest total cost. And the optimal solution is basically this kind of transition. Okay, so we're going to have generator 1 on at this point. We're going to turn generator B on. For hour 2, we're going to turn generator B off for hour 3. Okay, so this is our optimal solution. Okay, so this is how we get the multi-period solution for this, basically. Okay, how we look at for more than one time period. Okay, this is our multi-time period solution, right? So this is a quite sort of graphical solution. And doing this is actually fairly intuitive for a small system, because you can see that it allows you to write out all possibilities and do things sort of stage by stage. You write out, what are the operating costs, what are the startup costs for each transition, and then you add up along a path to figure out at the end of the day, the total cost. Then you pick the lowest total cost. So this works for small problems. If you have 4 or 5 generators, this is not a bad way to solve the problem. But the issue is if it's not small, if the problem is fairly large, then this sort of graphic way of solving the problem, or the technical name is dynamic programming, it doesn't work because there's way too many possibilities to think about. So the number of paths we have turns out to be again exponential in the number of units and the number of time periods we have. And so there's too large. There are too many passes for us to think about. Okay, so this sort of good illustration of one way to think about unit commitment for multiple time periods, but again, that's not really the algorithm we use in practice. Not really the algorithm we use in practice because the system can be potentially very large, right? But this does give us a feeling of how to solve this kind of problems and all the complexities that may arise because there's sort of minimum up, minimum down, this kind of constraints on the right, this kind of constraints on the generators. Any questions about this procedure? Okay, so there's no questions, then let's take a break. Then we come back, we'll look at the electricity markets. Okay, so the last topic we'll cover in this class, we'll look at how markets work and how money exchange happens. Right, so we covered a lot about unit commitment. We cover about economic dispatch. Our viewpoints has always been on that we have some central operator that just solves the whole problem. And that's really not how the market works. It's not, if you're a generator in the market, it's not, you're not directly being controlled by a central operator. So, for the last part of the class, we'll look at, at the high level of how electricity market works. Right? If you own a power plant, how do you participate in the market? And how does money exchange hands in the market? So let's take a break now. And then we'll be back at 10:30. Okay? Then we'll be back at 10:30. We'll look at how electricity market works, our systems.
Can I ask a really quick question to clarify something?
Sure, go ahead.
On slide 46, it might be actually a bit later for the initial state where we first define the initial state. My question is, do we assume that that initial state is the absolute starting point, or could it be that the initial state was, the state maybe for 2 or 3 hours? Because in that case, then the transitions for A are possible, right?
No, so the initial state is just the initial condition of the problem. So it's just the absolute initial state. It's what's given in the problem. There's no choice for initial state.
Okay. My question is, because could it be that that initial state was on for maybe a few hours and then we begin doing this?
Oh, that, okay, yeah. Yeah, so normally that will be given, but here we're going to, for our purposes, we'll just assume the system just starting there from scratch. So
Okay.
Time starts from the initial point, yeah.
Okay, sounds good, thank you.
Professor, I actually had a question as well.
Sure.
So when I think this might have been really similar to what he just asked. So if we're like we're using, say generator A in the first hour, and then in the third hour, we're using generator A again, do we have to pay the startup cost twice?
No, so startup cost only is paid when you transition from off to on.
So even if you're not using it in the second hour where it has no load?
Yeah, so even if you're, A has load, right? Does A not have load?
No, it does in this one. I'm just saying, like in a hypothetical problem.
Oh, hypothetical, yeah. So if it's on and has no load, you pay the no load cost, but not the startup cost.
Okay. And how are we differentiating between those two costs? Are those given with like the cost equations for each?
Yeah, generator? Those will be given. Those are sort of the parameters associated with a generator. So like you can think of, coming from the data sheet of the generator.
Okay, because so far it's been like the no load cost was the like the C value, like the A.
Right.
AX.
Yeah, that's C value. Yeah.
So then the startup cost would be a separate kind of just given this is how much.
Yeah. It'll be another parameter. It'll be saying, the startup cost is this.
Okay. All right. Thank you.
Professor?
Yeah.
Do you mind going over again? How do you eliminate the purple path? In this slide.
How do I eliminate some of the paths?
The purple path.
So the purple paths are all the possible ones, right? So what we want to do is we want to eliminate the ones that's not possible. Right? Okay. So for example, if you look at, so at this stage, now these are the paths we have. We want to, some of them are not possible because of the minimum on time conditions, right? So let's pick a particular path, okay? Let's say let's say we're going from this blue dot. Let's say we're going from this blue dot to this blue dot, okay? From time period hour 1 to hour 2. Or yeah, let's pick that one. So this requires us to go from 0, 1, 1, right? This requires us to go from 0, 1, 1 to something like 1, 1, 0. So we're going to go from this dot up here. Okay, so this is 0, 1, 1 to 1, 1, 0, right? So the question is, why is this not feasible? Because what happens here is we turn generator A off, right, in this transition. But then we're given that if A is turned off, A must be off for 3 consecutive hours. So you cannot immediately turn it back on again. So that rules out that path. Because that requires turning A off and turning A back on.
Oh, so when we turn, so like the data is given, like the TD and TU is like
Yeah,
given.
so those are all given, right? These are sort of given in the generators, right? So we have the minimum uptime, minimum downtime,
Oh, okay.
no low cost, startup cost. So this is a table, right? This is a table.
Oh, I see.
Yeah.
Got it.
So yeah,
Thank
so
you.
there always a table that gives all the information.
So when we turn A off, it has to be staying at off state for 3 hours.
For 3 hours,
That's
yeah.
why
So
the pass doesn't work.
yeah, that's why that pass doesn't work. It violates this condition.
Got it.
So then that violates what I was just saying then about how if that was a path where A was on, A was off, A was back on again, right, for 1, 2, and 3. And then you don't want to do that. Well, essentially what I'm saying is you're not going to leave A on the whole time then, because you don't want to pay the no load cost, right?
Right, so but that depends on what the no load cost is though, right? So sometimes maybe the best choice is to leave a generator on and not generate very little power. Right,
Okay,
so
but you didn't consider it in this one. It was like just because the no load cost is high.
No, so here the no load cost is 0 for this particular, right? So the procedure is to figure out all the feasible possibilities, then look at the cost, right? So
Okay.
what we've been doing is just eliminating all the infeasible ones, right? So this eliminates some of the possible combinations because they cannot meet the load. Then we start eliminating passes because they don't satisfy the minimum up and minimum down conditions.
Right, but couldn't you have left A on the whole time and it wouldn't have had to?
Yeah, so our final solution was leaving A on all the whole time. Right? Our final solution was A is always on.
Right, but wasn't there like one option where you had A was on, well, A was being used during the first hour and the third hour, but not during the second hour. But you could have left A on the whole time.
Yes, here we're leaving A on the whole time. A was never turned off for us.
Right, we're using A the whole time, right? It's generated.
Right. Yeah, so there conceivably could be possibilities where A is on the whole time but not used. That's very possible in practice.
But those get thrown out early on in the problem when we're looking at feasibility. Because it was thrown out because it had a downtime of 3 hours, and since it wasn't being used in one of the paths, it wasn't being used during the second hour. It was thrown out because it would like have been turned off.
Right. So, but turning off and leaving it on and generating no power is different, right?
Right.
So that depends on problem data. It's very dependent on the problem data and the exact load and the no load cost.
Okay.
Yeah. So it's very much the problem dependent. So in this case, we did not have that possibility. But if I change the data, we could easily have had that possibility.
Yeah. Okay. That makes things a little bit more complicated, doesn't it?
Oh yeah, things are very complicated in practice. This is a very simple illustration.
Yeah.
In practice, you have minimum up, minimum down. You have ramp rates. You have startup cost. You may have shutdown cost. You have all those kind of different things. So that's why in practice we don't draw this kind of arrows because it gets way too complicated. Very quickly it gets very complicated. Yeah.
I get it. Thank you.
Yeah. Okay, all right, so let's get started, and we're going to look at the electricity markets. So electricity markets is actually quite a strange market. Okay, this is not common to have a market like the electricity market. It's quite sort of different than other things we have in the world, and the reason that the electricity market basically couples the physical delivery of power and the financial settlement together. Okay, it's actually quite interesting. It's sort of different than any other commodity market we have. So for other commodities, like say, let's say you're either buying food or you're buying, let's say you're buying computers or cell phones, things like that. the physical delivery of the thing and the financial transactions are often not very coupled, right? So if, for example, you can buy, you can buy a computer, you can pay money now, and the computer gets to you, which people ships it, maybe gets you in a week, right? So the money exchanging hand and the actual getting the commodity to the consumers are very different. Okay? The shipping of the commodity and the money has almost nothing to do with each other. However, that's not true for electricity. Okay? Electricity is its own special kind of market, where the physical delivery, right, getting power, so getting current, getting electrons to people, and the financial market is tied together. Okay? It's very much tied together. Right? So in some sense, the financial market cannot be really decoupled from the physical delivery of the good. Okay? So that's the interesting thing of this. Right? And really, what we have is, the physical delivery happens very fast. Right? So anytime we need a demand has to satisfy. Okay? So the generation must equal to load at all times. Generation must equal to load. So this is interesting, quite interesting. And also that the failure imbalance, so failures can lead to the collapse of an entire system. Okay? So the failures can lead to collapse the entire system, right? So this is also unlike other commodity markets, because if you think about, let's say, other things that's balanced, at all times, for example, internet, right? Let's say we're all, this is virtual, you're viewing this lecture is possible because the internet is balancing demand of data. But the internet doesn't go down if one part of the supply and demand is not balanced. Okay, so for something like the internet, you can take out, one load or one generation. The other part of the system still works. Not so much for power. And so power demand, supply and balance must be balanced across the entire network. And the whole thing must be balanced. And the whole thing must be balanced. So this is where the physical delivery has to match supply and demand all the time. It has to match supply and demand all the time. And this has to happen over all time scales. Happen over all time scales. Okay, so this is a very special market. It's a very special market. And we sort of have to think about how money exchanges happen, right? Okay, so at the end of the day, what we want the electricity market to do, the electricity market actually has two jobs. One is to match supply to demand, so do resource allocation at a very fast time scale. And the second, what the market has to do is the market has to basically somewhat guide how does money exchanges happen. If you are a generator, how do you get paid? If you're a load, how do you pay people? Okay, so this is what the market does. So the market is a fairly complicated market. There's a lot of mechanisms around this market. But we are going to look at a very idealized design of the market. That sort of forms the foundation of how how the sort of practical, very complex market is built. So we're going to look at sort of the idealized version of how electricity market, how we think it works. So so another difference between the electricity and other commodities is we're going to pool all the electricity that's being generated. We're going to pool all the electricity, right? Again, this is not very similar to the internet, right? So for internet, the data is not pooled, right? So we have different people demand different data. However, for electricity, for power, we're going to pool all the electricity. Okay, we're not going to distinguish electricity. Okay, so what practically this means is that generators cannot pick consumers. Okay? And consumers cannot pick generators. We cannot pick. There's no way to differentiate the electricity generated by one generator from the other. That's not that's very difficult to do. That's very difficult to do. Okay, so we're going to pool all the power. We're going to pool the generated power. And the good thing is that this basically couples all generators and all demands. Okay, this is basically couples all generators and all loads. Okay, so since we cannot distinguish the power generated by different generators. So when the market operates as a very short-term scale, when we do resource allocation, of how much generator generates, how much to satisfy the load, normally we cannot have a constraint. That says generator A, 80% of the power from generator A has to go to load 1. That's normally just not possible. It's not a constraint we can enforce in the system. Okay, so our system, basically the power system is a single commodity because power is a single commodity. We cannot distinguish between the commodities. There's a single commodity market that has to be balanced across the entire system. Okay, it's a single commodity market, a single seller, single buyer, and the transmission network basically pulls all the resources together. Okay, so it's a quite interesting market, and that it's not seen at other places. Right, and another sort of the difference between difference between the power and other things is we do have variations. Okay? So seasonal variations is not uncommon. Okay, almost all commodities have seasonal variations, right? So especially for things like, for example, food, right? So it has very strong seasonal variations. Things like food, clothing, there's variations. The issue is there's no easy storage. Okay, we cannot store at large quantities. Okay, we cannot store things in large quantities, right? So, for example, for this class, we're going to, so we have a lecture, but this lecture is uploaded onto YouTube, and that's a form of storage you can look at later if you want. But electricity, we cannot. Okay, there's no way, no easy way to store in large quantities. Okay. Right, so we must, we all must always meet demand, and there's a very low price elasticity for the demand. Okay, there's sort of very low price elasticity for the demand. Okay. So what this low elasticity means is this, right? So if you look at this as power, so think of in megawatts. If you think of this as a cost curve, this is cost. So as we generate more power, this is, let's say this is $, we'll have more cost. So the cost is higher when you want to generate more power. what does the demand look like? If you're going to draw the demand curve, what does the demand curve look like? Right, so cost curve is the amount of money it costs to generate power. What does the demand curve look like? What is the amount of demand? How do we relate the amount of money we're willing to spend for a particular demand in relationship with the demand?
Exponential decay.
It's really not an exponential decay, right? Right. We don't think of, whenever you turn on the lights, you're not going to think of, oh yeah, if the cost is a lot, I'm not going to turn this light on. That's just not how we think about it. So it's actually not exponential decay. So what does the curve look like? It's not something like this. It's not very smooth. Right? So it's not sort of this sort of continuous decaying curve that you see from sort of this macroeconomics. Right? Think about it. It's not really, again, not a concave downwards parabola, right? So these are, these are curves that capture the fact that you're willing to consume less if the price is high. That's not how power is thought of. Okay, that's not how power is thought of. The demand curve really looks something like this. It's basically something like this. It's almost a vertical line. This is demand. And this is almost vertical. What this says is, I want this much demand. I don't care what the price is. Okay, so demand works in the power. It works in the electricity market. Basically saying, I want 100 megawatt. I don't care what the cost, right? So us as consumers saying, whenever I flip a switch on, whenever I plug something in, I expect I will get power. That means my demand is not sensitive to the cost at all. So the way, basically, the way we behave, right? So we are the demand, right? Customers, we are the demand. And we say that we expect power to be on all the time, meaning that I have a vertical line. I want this much power. I don't care about the cost, right? So this is how demand works. So this is says there's very little elasticity. Okay, there's very, very little elasticity in our demand. Right? So we are not very, so that means the demand is not price sensitive. We're not very price sensitive. Any question with this picture, supply and demand? So later we'll draw some pictures where the demand is more sensitive to cost, but in actual reality, demand is not very sensitive to cost at all. Like our basically demand is driven by our daily behavior. We don't think about the cost of consuming power. Then that's just not. That's just demand is just almost vertical down the line. All right, and this actually breaks a lot of economic theory, because this vertical line essentially have infinite derivative. Okay, so that this makes life complicated for theory, but that's the way power works. Okay? That's the way power works. Right. Okay. And this market also happens in different time scales. And this market often also happens in different time scales. Basically, if you think about time of delivery of power, okay, we have the seconds time scale, to hours, to days, to years. So there's multiple time scale this can happen, right? So for example, if you're a generator, you want to think about your year, right? So let's say you're building a large generator. Then you're counting on this generator to make money over years of time, right? Over decades. Okay? But then if you're a system operator, you also worried about the second-to-second balance of demand, okay, with second-by-second balance of demand. So what we will look at is a spot market. Okay? We'll look at what's so-called a spot market as a second by second here. So a spot market means the market that's happening right now. Okay, meaning the spot market, meaning the market that's happening at a particular instance in time. Okay, for example, at this hour, we want to make sure that generation equals demand. So this is our spot market. Then the other markets, this is sort of structured on top of the spot market. So we'll first understand how the short-term power balance work. Then we'll look at the sort of the longer term, how this is, how the other ones are structured on top of the spot market. So the spot market for electricity really is a sort of the balancing of supply and demand. Okay, so I have some demand, I have some supply. I want people to balance the supply. Well, we want to balance the supply and demand. And the question is, can we have negotiations? Right, so normally when you think of the market, you think of negotiations, right? You think of shopping around for different buyers or shopping around for different suppliers. For example, if you're buying a house, you're going to look at many houses, right? And you're going to make an offer, and they're going to decide. They're going to have many buyers. They're going to decide things like this, right? So this is called negotiation. So normally a market consists of a negotiation process, right? The buyers looking for suppliers, the suppliers looking at different buyers, and eventually, people work things out. So for power, can we have this kind of negotiation? Are there real-time negotiations happening in power systems? Does Seattle City Light go to negotiate with different generators to figure out how much power they supply at a very short time scale?
I'm gonna go with no.
Right, so obviously there's no negotiation, right, every day. Okay, right, so the city light is not going to wake up every day and say, okay, for the next hour, let me go and negotiate with a bunch of generators, figure out how much I should buy from each, right? So that's not how power system works, right? Because this is too slow and too sort of expensive. Okay, so each of us is not going to negotiate with all the generators. Okay, so really, this is not a. So at the very short time scale, or at the sort of the bottom level, there's no explicit negotiation between buyers and sellers. Okay, so this is also different than a regular market. A regular market, when you go to buy anything, there's normally a negotiation process, right? There's normally a process when you can look at many suppliers of the same good, right? Whenever we go shopping. However, for power, this is not the way it works, right? So power, what works is there's a managed spot market. Okay, so we're not going to have a pure market where negotiations can happen and people can shop around. That just doesn't make sense for the physical delivery of our system. Okay. So our physical delivery system, basically by working, our physical delivery system we'll have a system generator. We'll have a system, also have a system operator. And what this system operator does is this system operator basically determines the allocation. Okay, determines the allocation. So the system operator has a final say of how much a generator should generate and how much load, how much sort of demand we get to consume. So this is the security of the system, which is supply equals demand. Okay, so this system operator basically figures out the allocation of the generator and demand to make sure supply equals demand. So how does this system, right? How does this system work, right? So this has to follow it has to operate with sound economic rules, right? So this system operator basically needs to have rules that make sense, right? For example, the system operator cannot just allocate, they cannot just pick up the most expensive generator, right? And make people pay money because they just decide to use all the expensive generation but not the cheap ones. So the system operator must have a market that makes sense, right? The people who are willing to be in the market, right? But then it needs to run very fast, so it cannot allow negotiation. There's no explicit, so this is not a true market. Right? Because there's no interaction between buyers and sellers. Okay, so this is not a true form of interaction. We as buyers of electricity, we never get to talk to the generators directly. Okay? This is just not in the spot market, right? Everybody goes through a middleman. This middleman is the system operator, and the system operator's job is to figure out a set of rules that makes people happy. Okay, so this system operator as a middleman needs to clear the market in a reasonable way that people are willing to listen to the system operator. Right. So basically what system operator does is it takes a bunch of information, on how much generation I have, how much load I have, how much can I increase production, can I decrease production, can I decrease load, can I increase load. This thing figure out a way of changes in generation, and then figure out the spot prices. So this is the prices that we have that used to determine payments to generators. Okay, so this is our spot market. Right. So any question, at least at a high level, of how the spot market works? Right. So this is basically a system operator as the middleman that clears this market. Okay. So this is the spot market, and this market goes on at least every hour of every day, if not faster. For some systems, this goes on, every 15 minutes or so. Right? A very fast market. So the well-functioning of the spot market, right, of course, is very important, right? There's, there's the big legal framework basically nowadays that makes sure that the spot market works out well. Okay, works out well. So if you are a generator, right? Let's say if you are a generator or you're a buyer, do you see some drawbacks from the spot market though? The spot market is necessary because I need supply to the demand. But do you see some drawbacks? If you are always in the spot market, is there something that you are, unhappy about this market? Could you be unhappy about this market? Are there some drawbacks? There are some things, let's say you're a generator and you're just in the spot market. Are there some things you are willing to do differently than necessarily what the spot market tells you to do? Should the spot market be the only market we have? Like, should we just operate, hour to hour with this market? So if you're always in the spot market and you look at the price it gets, Is the price very stable or very volatile, do you think? Is the spot market price all that stable? Like your generator, you're trying, it's a big investment, right? So hundreds of millions of dollars. And you're living this spot market. Right? So the issue is the spot market price are quite volatile. There's quite a bit of variation in the spot market. There is quite a bit variation, okay, in the spot market, right? It looks like the stock price. It's actually, not very dissimilar from the stock prices. Goes up and down all the time. There's big spikes. There's big drops. Okay? So there's not so it's a lot of uncertainty associated with this. A lot of uncertainty if you just play in the spot market. So most participants actually wants more certainty. Okay. Right. So like you, if you have some savings, you're not going to put them all into the stock market and just write it out. Right? So a lot of participants want more certainty. So how do you get more certainty? Right. So how do you get more certainty? Basically, there's trading ahead of the spot market. Okay, so the spot market is always operating, right? Because that needs to figure out the physical delivery of electricity. The spot market is always on. However, the price out of there can be quite, volatile, goes up and down, right? Sometimes it's negative, sometimes it's, $9,000 per megawatt hour. So there's a wide dynamic range of the price. So to be more certain, then trading is allowed between different participants. Okay, so they can trade ahead of the spot market. And then if they agree on some trade, basically the spot market just acts on top of this trade. Right, so there's a trading. There's some trading allowed into this. Right, so we're going to look at basically how trading works. Okay, we're going to look at how trading works. Okay, so there's two ways for trading ahead to work. So one way is so-called the pool trading. Okay, basically it's you still have an operator, and this operator job is to figure out how trades happen over a long term. And they're so-called bilateral trading. They're called bilateral trading. Okay, so pool trading. So how does pool trading work? Right, pool trading works by all the producers will submit some bids, all the consumers submit some offers, and then we still have a market operator that figures out this sort of bids and offers, right? So this is an operator. So there's bids, there's offers, and this is the settlement. Okay, so the way this works is this just a sort of a longer term version of spot market, right? Instead of clearing this spot market being clear hour by hour, pool trading you may have something that over days and months, right? So like if you're let's say a nuclear generator, you want to say, okay, I can deliver this much power at this price, and if you're load, you can go into say I'm willing to pay this much. I'm willing to pay this much for this amount of load. And then the operator will just come in and basically ask the middleman to settle this kind of trading. So this is sort of the centralized pool trading along this way. And this is how a lot of times the North American electricity market works. Okay, so we'll have a spot market. Ahead of spot market, we'll have some pool trading. And through this trading, we'll try to balance supply and demand. through this trading behavior. We'll try to get some longer term certainty, right? So you can, you can think of this as a futures trade. And then another way to do this is called the bilateral trading. Okay, so it's bilateral trading. Yeah, go ahead.
Quick question. So are spot markets sort of like localized small scale markets? And then pool market?
No, spot market is not a small scale. Spot market has to clear all the generation and all the demand.
Okay,
so
but
it's just for one time. So.
Okay, but I guess what I'm wondering is it's more for like small scales, like on a per city basis, correct?
No, spot market is very large. Spot market is quite large. For example, think of the largest spot market we have in the U.S. is PJM. So that's it's called, PJM is Pennsylvania, Jersey, Maryland, but sort of much larger around than just those 3 states. And they have about 100 million customers.
Oh, okay.
So it's a giant market. It's not that small. I think of a spot market as like the stock market, right? It's a giant market that clears a lot of things. So it's definitely not small. Pool trading, if you look at the bids and offers, are the smaller scale thing. For example, city of Seattle may have one offer into the pool, right? So there's a lot of small customers around, and each of them have some bids, have some offers, and they just give it to the to the operator and say, please clear this bids and offers. But the scale of the market is gigantic. Like this is trillions of dollars being cleared in this kind of thing. So it's not small in any sense.
Okay, thank you. Yeah, makes sense.
Yeah, so the participants may be small, right? So if you look at the FERC order, so FERC is the federal regulatory body. It regulates how electricity market works. So FERC is allowing very small players to enter the market. It's, for example, a building nowadays can conceivably enter into the market as a participant. So you as a building may say, okay, I want 100 kilowatts of power at this hour. That's possible, but the total volume of trading is quite large, right? So again, as a stock market, you can buy a single stock on the market. That's fine. It's sort of right. You can buy the index. You can spend $100 on buying an index. That's okay, but the total volume in aggregate is quite large. This is not small. Okay. So the other alternative to this pool trading is you can have bilateral trading. So this pool trading to some people is too centralized, right? So if you're a true believer in the free market, then there's some drawbacks with the pool trading, right? There's some drawbacks. Okay? So the drawbacks is, right? So if you look at this pool trading, so if you're a supplier or demand, can you think of some drawbacks? Are there some drawbacks associated with this? Right? If you're designing the market, there's some reason you will not be happy with this kind of pool trading. Right? So if you this kind of pool trading, if you give the bids and offers to an operator, these are not private anymore, right? So often when we buy sell stuff, right, you want your bids and offers to be private. But if you go through a central operator, they're just not private. There's no way it's private. Right? The central operator has to take the information and just clear this. Right? So this is now, it's not public, but somebody knows this. The government basically knows how much you're willing to pay to generate power or to consume power. Okay? So this is not very private anymore. So then people said, okay, I'm not happy with this, right? Why do I need to go through a government? Basically, why is the government regulating this by knowing all the information and clearing it? But then people came out with this sort of bilateral trading. So this bilateral trading, there's only two parties. Okay, so this is a seller and a buyer. Okay, seller and buyer. And trading, basically, this is a private agreement. Between them. Okay. So the price and everything, the amount, the price, how it's delivered, all that is entirely up to these parties. Okay. It doesn't, doesn't have to make sense necessarily. It doesn't have to be cheap. It doesn't have to. Basically, you just need to agree on some numbers out of bilateral trading. So this is actually standard European approach. Okay, so this is a standard European approach. So when the power system market was first being developed, the US, the North American market basically settled on pool trading. We have centralized entities that clears bids and offers. Where the Europeans thought, we'll just do everything bilaterally. We'll just, come to private agreement. So you just tell the government, generator A decide to load 1 gigawatt of power. That's all you need to do is tell the government. You don't need to say anything else. Right? So this is sort of two different ways of approach. And of course, nowadays is much more, so nowadays is much more complicated. All the markets are much more advanced. There's both North American and European, there's a mixture of, pool trading and centralized pool trading and bilateral trading. There's complicated futures being bought and sold all around. The electricity market is not a small market. So all, for example, banks and hedge funds and all will have a division that sort of trades electricity markets. And obviously these people are not, a bank is not going to generate power, but there's big trade, they're still trading this commodity market. So, if you guys are interested in this kind of financial markets, there's a lot of opportunities in this sort of financial institution that trades this kind of market, trades this kind of electricity, trades based on electricity contracts. Okay, so now you can package bilateral tradings to sell to other people. You can play different games within pool trading and all of that. So it's quite an active area in figuring out this kind of things. But the overall picture is we basically have a spot market that determines the physical delivery. So that's always there. You always need a spot market that just at every hour, let's say, determines how much generator should generate, how much demand should consume. On top of this, we can build longer term time tradings as either pooled or either bilateral and sort of mixture of that. And then people can go from there. Okay, so that's always sort of built. But at a high level, that's how the market works. So any questions with that? Yeah, so the electricity market is quite interesting as its own field. And the FERC is an important regulatory body in the US. And so there's a big amount of money being exchanged when you trade this kind of thing, right? So it's not small money. So for example, 3-4 years ago, I think JP Morgan Chase got fined a couple billions of dollars for not playing games in trading, right? Playing sort of doing illegal things when they're trading electricity. Okay, so there's interesting both from the regulatory side and from the the market side, the speculation market side. Right. So I guess to finish today's class, right? So let's think about based on this market. Can you guys think of games you can play in this market? So if you're a trader in this market, what kind of, how do you want to trade in the market? I say we're going to try to maximize your profit. Are there some ways that you can maximize your profit? So if you work for a company that trades and sells electricity, how will you do it? What are the opportunities to make money in this market? Right. So one way to make money in this market is basically, remember in stock market the price is quite volatile, right? So if the demand is high, then the price is very high. If the demand is low, the price could potentially be negative. Right. So the idea is the goal is to time this correctly. So you want to, through trading or through bid and offering, you want to basically time it such that you have generation when the demand is high, when the price is high. And when basically you want to say you want a lot of generation, you want some generation capability, a lot of generation capability when the demand is high. And you don't want to be holding a lot of generation when the demand is low and the price is low, right? So all the market comes down to basically timing it correctly. If you want to time this correctly, and market design comes down to not allowing people to play this kind of games, right? So it's always a balance on whether there's a lot of volatility, and another way is you try to make sure that the market, from a system operator point of view, or from market design point of view, you want to make sure the market behaves well, right? You don't want the market to be very volatile. But to make money, to make trading happen, you need some kind of volatility in the market. So that's the sort of the design question of the market. So next class, I guess, of looking ahead to next class we'll finish markets by looking at a simple example. Then we'll do a review for the final. We'll do a sort of brief review to look at what kind of topics are on the final. Okay, so no question here. We'll stop here today, and I'll see you again on Wednesday.